Till now we have seen the state equation x dot of t is equal to ax of t plus b u of t. All of these are in the matrices form, right? We will now try to find out the solution of this equation. That means what is the value of x of t, okay? Not only when the input is given, but also in the presence of initial conditions, okay? So, initial conditions as well as input, if it is known, then what will be the solution x of t. Remember that all of these signals, they are in the matrices form. So, if there are n state variables, let us say x1, x2 and so on till xn are the state variables of the system that we are considering. Then what will be x dot of t, x1 dot, x2 dot of t and so on till xn dot of t, and this is equal to the matrix A, and here the state variable matrix xn plus matrix B into the input u of t, okay. Now here this matrix which we call as the state vector, right. So this is what we have to find out. For this we will make use of the Laplace transform. Okay, so if you apply the Laplace transform to this equation, what will you get? S into x of s minus x of 0, the initial value, is equal to a into x of s plus b into u of s. Okay, so what are these x of s and everything? Just for the sake of clarity, you can write this once again. X of s is the matrix x1 of s, x2 of s and so on till xn of s, right, where x1 of s is the Laplace transform of x1 of t. Okay, similarly x2 of s is the Laplace transform of x2 of t, like that. Okay, so because it is, we are writing in the form of equation, you should not get confused as to whether this is an actual matrix or a simple single signal. Okay, and what is x of 0? Where x of s is this and x of 0 is, it is not the Laplace transform, but it is x1 of t is equal to 0, x2 of t is equal to 0 and so on till xn of t is equal to 0. Okay. Similarly, x of s is the same as this, and u of s, if it is a single signal then it will be u of t. If it is multiple signals, multiple inputs, then it will also be a matrix. Now you can get x of s on one side. So what will you get? S into x of s minus a into x of s is equal to x of 0 plus b u of s. Okay. So this can be further simplified as si minus a, I is the identity matrix, into x of s is equal to x of 0 plus b u of s. Okay. So then what will be x of s now? This is going to be si minus a inverse x of 0 plus si minus a inverse b into u of s. Now we can apply the inverse Laplace transform. Then what are you going to get? The state vector x of t is equal to L inverse, that is the inverse Laplace transform of si minus a inverse into x of 0 plus the Laplace transform of si minus a inverse b into u of s. So we could write this way because L inverse of two functions f1 plus f2 is nothing but the sum of the Laplace transform of the individual functions. Okay. So now this is the final solution, and you can see that this part is due to the initial conditions, and because of that it is known as the homogeneous solution, or you can also call it as a natural solution. And what is this part? It is due to the input and it is called as the forced solution. Okay, so we can divide into two parts. So you can write the different names as well here. In the exam, whatever name is given, you will be able to understand. It is also called as the natural response, or you can also call it as the free response. Now we have seen the solution of the state equation using the Laplace transform. Now we will see what it is in the time domain. So that means x dot of t is equal to ax of t plus b u of t is the state equation, and remember always these are all matrices. Okay. Now first step is you can rearrange as x dot of t minus ax of t is equal to b u of t. Now multiply both the sides with e to the power minus a t. What is a here? A is the system matrix, right? In the equation you have here x dot of t is ax of t plus b u of t. So the same a you are using here. Okay. Now you might get a doubt, how do we put the matrix as the power of something? Okay. So we know that e to the power x, it can be expanded as 1 plus x by 1 factorial plus x square by 2 factorial plus so on, infinite series, right? So that is what we are going to do here. Instead of the normal power, you are having a matrix. So here you are going to write 1 plus e to the power minus at by 1 plus at whole square. So you will do multiplication of the matrices. That is what this term means. Okay. So then what are you going to get here? E to the power minus at x dot of t you can write as dx of t by dt minus ax of t is equal to e to the power minus at b u of t. One thing I want to stress again and again, that here x of t is not a single function. Just because we are writing d by dt of x of t doesn't mean it is a single function. It means that for an entire matrix each of the elements we are differentiating. This is only for the writing purpose. Alright. So now this you can write as e to the power minus at into dx of t by dt minus e to the power minus at into ax of t is equal to e to the power minus at b u of t. Now what we can do is, the left hand side we can write as d by dt of e to the power minus at into x of t, right? What is d by dt of f1 f2? This is equal to f1 df2 by dt plus f2 df1 by dt. So here in our example, if you take e to the power minus at x of t, if you take this as f1 and this as f2, now if you have to differentiate them, what are you going to get? E to the power minus at dx by dt plus x of t into minus a e to the power minus a t. This is the result you are going to get, right? So that is what you have here. E to the power minus at dx by dt is this first term on the LHS, and here you have minus a e to the power minus at into x of t. That is what you have here. Okay. So now this is equal to e to the power minus at b into u of t. So now if you integrate on both sides, integrating on both sides along with limits. Okay. So we will take the limits from t naught to some time t till whichever point of time we need. Okay. So this is going to be e to the power minus a tau we will write, because the limits we are taking from t naught to t, into x of tau. This is from the limits t naught to t, and this is equal to integration again from t naught to t. Wherever t is there you can replace with tau. E to the power minus a tau b into u of tau d tau. You are differentiating with respect to tau from the limits t naught to t, so that the final expression that you are getting you will get in terms of t, the real time t. Okay. So this is going to be e to the power minus a t into x of t minus e to the power minus a t naught into x of t naught is equal to t naught to t e to the power minus a tau b u of tau d tau. Now from here if you pre-multiply, that means ahead of each term we multiply with e to the power a t. So this order of multiplication is important because the matrix multiplication is not commutative. Okay. So pre-multiplying with e to the power a t on both sides is going to give you x of t minus e to the power a into t minus t naught x of t naught is equal to integral t naught to t e to the power, or you can write this inside the integral as well, e to the power a t. With respect to the integration, e to the power a t is a constant because here it is not in terms of tau, alright. So e to the power minus a tau b into u to the power tau d tau. Okay. So this is going to give you x of t is finally equal to e to the power a into t minus t naught x of t naught. So this, as you can see, it is the response due to the initial conditions. Initial time we have taken as t naught plus integral t naught to t e to the power a t minus tau b into u of tau d tau, and this is due to the input function. So what is this part of this solution? It is called as the homogeneous solution or the natural response or the free response. You write down all three of the names. And this is the forced response, which is only due to the input. Now instead of t naught, if you take initial time as 0 only, if t naught is equal to 0, then what are you going to get? X of t is simply equal to e to the power at x of 0 plus integral, and what will be the limits now? 0 to t e to the power a t minus tau b u of tau d tau. Okay. So this is when the initial time is taken as 0 rather than t naught. So you can write both these equations. This is for t naught and this is when the initial time is taken as 0.